Hi, in this video we will study the linear independence of vectors of an orthogonal set, and then later in the video we will introduce orthogonal bases. Well, let us assume that we have a set of vectors v1 up to vk which is orthogonal set of vectors, and this can be in any Rn. And we assume that all these vectors are non-zero. Okay. Then I'm claiming that these vectors v1 up to vk are going to be linearly independent. Means what? Means that if we have a linear combinations of these vectors, which is equal to zero vector, then I need to prove that the coefficients are going to be equal to zero for such a linear combination. To prove it, we are going to dot product both sides of this equation by v1. Okay, this is a trick that we will do again and again when we're working with orthogonal sets. Dot product of a linear equation by one of these vectors. So we have v1 dot c1 v1 up to ck vk equals to v1 dot 0. And well, if you expand it, you get c1 v1 dot v1 plus c2 v1 dot v2, and this will go up to ck v1 dot vk. And this is, well, the right hand side is 0. Dot product of any vector and 0 vector is 0. Well, here is now the orthogonality of the set v1 dot any other vector from that set is going to be 0. So c2 times 0 plus ck times 0, this is. But we don't know what is going to happen to v1 dot v1. So we are going to have the length of v1 squared. Well, it's not, well, it can be 0 or not, but we are assuming this is what we have. Okay, now that if you simplify, you get that this is going to be equal to 0. This implies that either c1 is 0 or length of v1 squared, or just length itself is 0. But this cannot be true because the vector v1 is not 0, so this cannot be true. This way we prove that, well, c1 is 0. We still have some work to do. We have to show that c2 is 0, c3 is 0, up to ck. All of them are 0. But similarly, we can prove that c2 is also 0. How? Instead of dot producting the equation by v1, you dot product it by v2. And we can show that c3 is equal to 0, and this will go up to ck equal to 0. And this way we have shown that 0 vector has only one way to be linear combinations of these vectors. And what we proved is proof of this theorem, that if v1 up to vk is an orthogonal set of non-zero. This is very important because we can have 0 vector in an orthogonal set. So if this is an orthogonal set of non-zero vectors of Rn, then v1 up to vk are linearly independent. Very nice. So non-zero vectors of an orthogonal set is, or they are linearly independent. Well, very nice. What would be corollary of this? The first corollary is that, well, if we're working in Rn, the maximum number of vectors that can be linearly independent is n. So this means that any set of non-zero vectors which is orthogonal vectors in Rn which is orthogonal has less than or equal to n vector. These guys, if these are non-zero and we are working Rn, since the maximum number of linearly independent vector can be only n, the number of these vectors cannot go beyond that. So we cannot have n plus 1 non-zero vector which form an orthogonal set. Well, for example, if you're working in R2 and any set of vectors in R2 with 3 elements or more cannot be linear and cannot be an orthogonal. So I don't need to check the condition. This set is not an orthogonal set because it has 3 vectors. In R2, the maximum number of elements of an orthogonal set, non-zero vectors, is 2, and so on. Well, the second thing is that, the second corollary is that if an orthogonal set of non-zero vectors in Rn has n vectors. So if we have an orthogonal set of non-zero vectors in Rn with n vectors, since we already know that they are linearly independent and we have exactly n of those, that means that if an orthogonal set is, then it is a basis for Rn. They are linearly independent and they have exactly n vectors. Any set of vectors which are linearly independent and have n vectors in Rn, this set is basis. And while these kind of bases have a name for it, so let me then write the definition. A set of an orthogonal basis for a subspace of W of Rn. Well, you can have also for different subspaces. So an orthogonal basis for a subspace of W of Rn is a basis. First of all, it needs to be basis for W, and it needs to be an orthogonal set. So orthogonal basis, each word has a name here, meaning yes, basis, it is a basis, and it is orthogonal. Well, later in another video, we will see that if we have an orthogonal basis for subspace, then writing vectors of that subspace as linear combinations of that set, that basis, is much easier than for a general basis.